Section 2, Basic Circuits. Chapter 6, Series Circuits. Chapter 7, Parallel Circuits. Chapter 8, Combination Circuits, Series Parallel. The three chapters that make up Section 2 provide a thorough understanding of electrical circuitry. Chapter 6 explains the principles of series circuits. You will take complex series circuits and reduce them into simple, solvable circuits. Chapter 7 explains several different methods for reducing and solving parallel circuits. The final chapter in this section, Combination Circuits, takes you step by step through a number of examples. When you have finished this chapter, you will be able to reduce any series parallel circuit into a simple series or parallel circuit. In all three chapters, typical circuits are presented with illustrations of proper troubleshooting techniques. These illustrations show how to use meters to locate open and short circuits. These sections should prove to be valuable for laboratory work, and they will assist you in comprehension. Chapter 6, Series Circuits. The objectives are to determine the total resistance of a series circuit, determine the voltage drops in a series circuit, determine the current values of a series circuit, determine the wattage values of a series circuit, apply Ohm's law to solve for known voltage, current, and resistance in a series circuit, apply the series circuit theory to assist in troubleshooting a series circuit. Some keywords and terms in the chapters are Kirchhoff's voltage law and series circuit. Chapters 6, 7, and 8 cover series, parallel, and combination circuits. Series, parallel, and combination are the only three ways an electrical circuit can be constructed. The combination circuit is simply a combination of the series circuit and a parallel circuit. These three chapters, when mastered, will provide you the basic skills to construct, analyze, and troubleshoot many electrical systems. 6.1, Series Circuit Principles. The series circuit has only one path for electron flow through the devices wired in the circuit. There are three formulas used to explain the laws of series circuits, as seen in the picture, where N is the total number of voltage sources, resistances, or current sources in a circuit. First one is voltage total, or ET, equals voltage 1 plus voltage 2 plus voltage 3, and so on. Resistance total, or RT, equals resistance 1 plus resistance 2 plus resistance 3, and so on. Current total, or IT, equals current 1 equals current 2 equals current 3, and so on. Voltage in a series circuit. Gustav R. Kirchhoff was a mid-19th century scientist who discovered that the total voltage applied to a series circuit is equal to the total number of individual voltage drops in a series circuit, as shown in the diagram or picture, where voltage total equals voltage 1 plus voltage 2 plus voltage 3, etc. This is known as Kirchhoff's law, or Kirchhoff's voltage law, as applied to series circuits. The source voltage of a series circuit is equal to the total value of each individual voltage drop. Figure 6-1 has three resistors wired in series with a voltage drop indicated at each resistor. When the three voltage drops are added together, they equal the source voltage. See figure 6-1. The total voltage is equal to the sum of the individual voltage drops. Current in a series circuit. The current in a series circuit is equal throughout the circuit. In figure 6-2, three resistors are connected in series to the source. Since there is only one path for the electron flow, the current must be the same value at any point in the circuit. See the diagram, where IT, or current total, equals current 1 equals current 2 equals current 3, and so on. The formula for series circuit current value is a mathematical way of expressing that a current value measured at any point in a series circuit is equal to the current value at any other point in that same circuit. If there are 5 milliamp flowing through R1, then there must be 5 milliamp flowing through any resistor or conductor in that circuit. See figure 6-2. In a series circuit, there is only one path for the current. Resistance in a series circuit. Total resistance in a series circuit is equal to the total circuit resistance combined. By adding the value of the individual resistors together, we find the total resistance of the circuit. See the figure 6-3, where resistance total, or RT, equals resistance 1 plus resistance 2 plus resistance 3, and so on. Figure 6-3 consists of 20 ohms, 40 ohms, and 60 ohms resistors connected in series. The total resistance value for this circuit is 120 ohms. Determining an unknown voltage. To find a single unknown voltage value, subtract the known resistance voltage drop values from the source. In figure 6-4, two resistors are wired in series. The value of R1 is 8 volts and the source is equal to 12 volts. To apply the law of voltages in a series circuit, subtract the known circuit voltage drops from the source. Power in a series circuit. The total amount of power consumed in a series circuit is equal to the source voltage multiplied by the circuit current. See the figure. Each device in the circuit that consumes power is part of the total load. An example of consumed power is the amount of wattage dissipated as heat by each resistor. See figure 6-5. Devices that are normally considered to consume power in a lab circuit are switches, fuses, and conductors. There are several methods for determining total power rated in watts consumed by a series circuit. In the first method, we multiply the source voltage times the current value of the circuit, E total times I total, or voltage total times current total. Another easy method is to multiply the current squared by the total circuit resistance, or I total squared times R total. It is very important to remember that the wattage rating of a resistor is not the amount of energy it uses. The wattage rating of a resistor is the amount of energy in the form of heat the resistor can safely dissipate without being damaged. In other words, a 2.2 kilo ohm resistor rated at a quarter watt does not consume 0.25 watts. A quarter watt is the maximum amount of heat energy it can safely dissipate without damage. 6.2 Applications and Troubleshooting Series Circuits. There are numerous applications for the principles of series circuits. This section demonstrates how to apply those principles and shows you the specific example of an airfield lighting system. In addition, troubleshooting series circuits is discussed. Applying Ohm's law to a series circuit. Ohm's law can be applied to any individual component of a series circuit. Look at figure 6-6. The Ohm's law formulas are noted at each location. If you do not know two values at an individual location, you can apply Ohm's law to find the third value. Example, if R1 or resistance 1 has a resistance value of 10 ohms and a voltage drop of 5 volts, then applying Ohm's law to the R1 location will give you a current value of 0.5 amperes. Could you go on from this point and calculate the amount of power used by R1? Airfield lighting system. An airfield lighting system has many miles of circuit cable. The system has miles of cable originating from the source of power to the runway, plus the distance around the runway itself. The only practical way to light a runway and taxiway system is to use the series circuit principles. Figure 6-7 illustrates how large the system may be. The voltage losses caused by the resistance of the copper lines do not permit a practical application of a parallel circuit. The lighting consists of a series circuit with a transformer located at each individual light location. The circuit is connected to a voltage regulator that maintains a constant amperage applied to the circuit. Since the circuit has a constant amperage at each transformer and lighting unit has equal resistance, each lamp will have the same voltage drop value. At times, the number of lamps in the circuit will change due to lamp failure. When the number of lamps changes, the amount of applied voltage from the regulator will change in order to maintain a constant 6.6 amperes applied to the circuit. By maintaining a constant 6.6 amperes to the circuit, Each lamp will burn at the same brightness regardless of how many lamps are lit at once and regardless of the voltage drop along the length of the conductor. See figure 6-8. Troubleshooting a series circuit using a voltmeter. A series circuit is really easy to troubleshoot. In figure 6-9, 3 resistors are connected in series to the power supply. A fuse is used for circuit protection, and a SPST or single pole, single throw switch is used to control the current to the resistor. One of the most common circuit faults in a series circuit is an open. A voltmeter, combined with the knowledge of the laws of the voltages, is a quick and easy method of analysis. There are several ways to locate a circuit fault. The following step-by-step presentation is not the only way to locate the fault. Lesson in safety. Remember, good safety is a habit that needs to be developed over a period of time. When troubleshooting even low voltage circuits, practice all safety techniques. Safety must become second nature to a technician when working on electrical circuits. To begin the troubleshooting process, measure to determine if there is voltage at the supply. Remember, a bad battery can still have a high voltage reading when it is not connected to a load. When checking the battery for proper voltage, make sure the switch S1 is closed. If the voltage at the battery is good, move to the fuse. Take a voltage drop reading across the fuse. A good fuse will not produce a voltage drop. A blown fuse will produce a voltage drop that is equal to the source voltage. Also, check the voltage drop across the switch. The closed switch should not produce a voltage drop. Figure 6-10, a single pole, single throw switch or SPST switch that produces a voltage drop when it's closed is defective. Next, check to see if there is a voltage drop across the individual resistors. If a resistor connected in series and a series circuit is open, it will have a voltage drop equal to the source voltage. The other resistors will have no voltage drop at all. A short circuit is another possible problem. If one of the resistors is shorted, that resistor will show a voltage drop of 0. The other resistors in the circuit will drop the entire source voltage. In summary, a series circuit provides only one path for current flow. In a series circuit, current is equal throughout the circuit. For example, I total equals I1 equals I2 equals I3, and so on. The total resistance in a series circuit is equal to the sum of all of the resistance values in the circuit. R total equals to R1 plus R2 plus R3, and so on. The source voltage is equal to the sum of the voltage drops in a series circuit. E total equals E1 plus E2 plus E3, and so on. The total power consumed in the series circuit is equal to the sum of the individual power consumption. P total equals P1 plus P2 plus P3, and so on.
End of Chapter 6. Chapter 6 Review Series Circuits.
This lesson contains a lot of formula-based computations, so get out your calculator and be prepared to brush up on your basic math skills. Make sure you understand how to find current, voltage, resistance, and power, because you'll need to be able to conquer these calculations throughout the remainder of the course. In this lesson, we will discuss 3 types of electrical circuits. In terms of wiring components, the 3 types of circuits are series, parallel, and combination. Before we delve into the circuits, let me show you a short list of what
some important symbols represent.
E is voltage, I is current, R is resistance, P is power, ET is voltage total, ER1 is voltage across
resistor 1
and can be more than one
resistor
and will be labeled in sequence ER1, ER2, ER3, etc. IT, current total, IR1 is the current across R1.
Resistance or resistor 1.
The same rule will apply if using more than one resistor. RT is resistance total, PT is power total, PR1 is power across R1. The same rule applies if you use more than one resistor. In a series circuit, figure 5.1, there is only one path for the current to flow. In a series circuit, there are certain rules you must adhere to. These rules will help you understand the circuit better. They will also make troubleshooting a lot easier. refer to figure 5.2 when reviewing these rules. Voltage in a series circuit is added. Kirchhoff's law. This means you must add all of the voltage drops together to get the total voltage. Looking at figure 5.2, you have to add the voltage drop across each resistor to get the total voltage, or ET. Current in a series circuit is the same throughout the circuit. This means whatever the applied current is, each component will see the same amount. Looking at figure 5.2, you have 5 amps, so every component will see 2 amps. Therefore, IT, current total, is 2 amps. Resistance in a series circuit is equal to the total ohmic value of all of the resistors combined. When looking at figure 5.2, you have to add 30 ohms plus 50 ohms plus 20 ohms to get the total resistance of the circuit, which is 100 ohms. Power in a series circuit is IT times ET, which is current total times voltage total. So looking at figure 5.2, if ET equals IT, which is 2, times RT, which is 100, then ET equals 200. IT equals 2, then PT equals 400 watt. There are other formulas to find power in a series circuit. Refer to the circle diagram of formulas from lesson 4. Use the formula for the known values.
Sometimes you have to solve for an unknown value first before you find another unknown value.
When you want to solve for unknown voltage value, just use the same for the formula, but use the current and resistance across that particular resistor. Example, in figure 5.2, ER1 equals to ER2, which is 2A, times R1, which is 20 ohms. So ER1 equals 40.
In figuring out the missing values from the previous circuit,
in figure 5.2, we used Ohm's law and we applied it to ER1. Remember Ohm's law, figure 5.3 merely shows us the relationship of voltage, current, and resistance. If you know 2 of the 3 values, you can solve for the other. Please take additional time to understand this formula by changing the values in figure 5.2 and solving for the unknown values using Ohm's law. Ohm's triangle in figure 5.3. Troubleshooting a series circuit
is best done
with a voltage meter. One thing to remember is most series circuits faults will have an open in the circuit. When an open occurs in a circuit, you will read ET, total voltage, across the open. An open is a break in the path for current to flow. The best instrument to troubleshoot a series circuit is a voltmeter. When referring to figure 5.4, if you put your meter across the switch, it will read however many volts the battery produces because it is open. If you push the switch down
in the closed position,
the voltage across it will decrease. With the switch pushed down
in the closed position,
if you take your meter and put it on each of the light bulbs, it will tell you the voltage drop of that particular bulb. If that bulb was open, the voltage drop across that bulb would read the battery voltage. In this type of circuit, there's only one path for current to flow, so no bulbs will light if you have an open in the circuit. See figure 5.4 again.
Review questions, Chapter 6. What does a voltage regulator do for the lights in an air-filled lighting system?
It keeps
the voltage total as required to keep the same current in all lamps, thus the same level of brightness. How much voltage will be found across a
good fuse?
No voltage or no voltage drop, since there is no potential difference between one end and the other end of the fuse. How much voltage will be found across a blown
fuse?
Total voltage or source voltage drop.
A blown fuse is like an open switch showing total potential difference.
In a series circuit, the current values are blank everywhere. They are equal everywhere in the circuit.
For a series circuit,
in a series circuit, the source voltage is equal to the blank is equal to the sum of the individual voltage drops. So voltage adds up
for a series circuit
to give you the total or source voltage. Blank is the total circuit resistance for two 25 ohm resistors connected in series. And for that, the answer is already shown, 50 ohms, since in a series circuit, if you have two equally rated resistors of 25 ohms, it must divide into the 2. So 50 would divide into 25
ohms.
When resistors of equal value are connected in series, they will develop a voltage drop of, as shown above, equal value. Two 25 ohm resistors connected in series will require a blank voltage source to produce a 6 volt voltage drop across one 25 ohm resistor. So thinking about this, 25 ohm resistors connected in series, what kind of voltage will it require to produce a 6 voltage drop across one 25 ohm resistor?
That would be 12 volts.
Since voltage drops divide equally in equal value resistors connected in series, so if you have 6 volts
plus 6 volts, that would be 12 volts.
So if you have equal valued resistors of 25
ohms,
you would need
12 volts.
Doesn't matter if you had
A 24 volt source,
then the voltage drop at each resistor would be 12 volts.
Use the series circuit values below to solve for the unknown value.
Here are the series circuit values. You can go ahead and draw this out. I may include the circuit diagram on this slide, but you can use these to draw your own. You have a total circuit current of
2 amps.
You have one resistor, resistor 1 rated at 8 ohms, resistor 2 rated at 4 ohms, resistor 3 rated at 12 ohms. Remember, these resistors are connected in series. This is a series circuit. There's going to be a few formulas involved. They're quite easy. Just follow the steps. First set, we want to find your
resistance total.
Formula is shown. The next step is to find your voltage total. Formula is shown. And your next step is to find your power total. Formula is shown.
Resistance total.
The total for that is 24 ohms. The values are given up top. For resistance, you just add those up. So your total resistance in a series circuit is your added resistor values. For your voltage total, again, you add your voltage drop. Since we do not know what each voltage drop is, we have to multiply your total resistance times your total current, which our total current is given up top in the problem, and we do know our total resistance, 24 ohms. So our total voltage is 48 volts. For power, we already know our total voltage, 48 volts, and we already know our total current, 2 amps.
Multiplied 48 times 2 is 96
watts. We next have to find out each voltage drop at each resistor, ER1, ER2, and ER3. We set them up as such. Again, for your voltage drop, you have to multiply your current at the resistor, which is the same at each resistor or the same as your current total, and multiply that by
each resistance value
at R1, R2, and R3, which are given up top.
First one
is 2 amps times 8 ohms equals 16 volts. Second one is 2 amps times 4 ohms equals 8 volts. Third one is 2 amps times 12 ohms equals 24 volts. Next, we have to find our current drop at each resistor. We already know that our current drop must be the same at each resistor, must be the same as our current total. So we already know our current total, so each resistor current should be the same, but we verify it using these equations. First one is 16 divided 8, 16 volts divided 8 ohms equals 2 amps. For the second, 8 volts divided 4 ohms equals 2 amps again, and 24 divided 12 equals 2 amps. So we just verified that it checks out using, again, Ohm's law formula. To find our powers at each resistor, we set them up as such, and we already know what ER1 voltage drop is. We already know what IR1 current is at each resistor. So we just plug in values, 16 volts times 2 amps
equals 32 watts.
8 volts times 2 amps equals
16 watts.
24 volts times 2 amps equals
48 watts.
This next problem is using the same concept. Use the circuit values below to solve for the unknown values. In this case, we give you the total voltage of the series circuit, 12 volts. Then we give you a new set of resistance values at each resistor connected in series. First, we find our resistance total, we find our current total, and we find our power total.
Resistance total
is 12 ohms. We just add the resistance values given up top for each resistor. Current total equals voltage total divided
resistance total.
So 12 volts divided 12 ohms equals 1 amp. For power, we multiply
resistance total
times current total. 12 volts times 1 amp equals to
12 watts.
We find out our voltage drop values at each resistor. We set these formulas as such: ER1, ER2, and ER3. For each one of those, we multiply
current total
times your
resistance at
each
resistance value.
In this case, 1 amp times 6 ohms equals 6 volts. The next case for ER2 is 1 amp times 2 ohms equals 2 volts. The next case for voltage drop by resistor 3 is 1 amp times 4 ohms equals
4 volts. Next,
we find our current values at each resistor. For resistor 1, 2, and 3, we set the equations up, again using Ohm's law, as voltage drop at resistor 1 divided by resistor 1 value. And the same for each one resistor, resistor 2 and resistor 3.
First resistor.
Current, we just divide 6 volts by
6 ohms. And those values are taken from
the ones that we have already found
and
the ones given in the problem. And that gives us 1 amp.
Next one.
2 volts divided 2 ohms
equals
again 1 amp. And again, we're just verifying that the current is the same in all
resistor locations.
Again, this is a series circuit, so the current is always the same at each
resistor location,
same as total. So in this case, 4 volts divided 4 ohms equals 1 amp. Finally, we find the power at each resistor location. We set them up as such for resistor 1, resistor 2, and resistor 3. Power of resistor 1 is 6 volts times 1 amp equals 6 watts.
Power of resistor 2 equals 2 volts times 1 amp
equals 2 watts. Power of resistor 3 is 4 volts times 1 amp equals 4 watts. Again, we already know what ER1, ER2, and ER3
are
from the problem set right there, the second set. So we just plug in the values that we already have at hand to find out. All we have to do is know the right formula or equation to use and plug in the values we already have little by little in a certain
sequence. That way
you use what you already have at hand. Thank you very much. This is the end of this
chapter questions.